Good morning, everyone. I'm Jimmy, and today I'll present my project on flood impact assessment and flood risk mapping of Typhoon Yagi. Let's dive in. So here is a quick overview of today's agenda. I'll start with the project's purpose, share a time-lapse video of Typhoon Yagi's progression. Then I'll share my maps about the typhoon's timeline and path that leads into my study area of northeastern Vietnam. Next, I will explain why I used Sentinel-1 satellite imagery for data for the flood mapping, followed by the image processing workflow in Snap. Afterwards, I'll talk about the flood impact results. Then I will explain the second part of my analysis where I use weighted sum analysis to examine the flood risk product. Finally, I'll conclude with a discussion on insights and future work before taking your questions. So the project's purpose, to understand the spatial extent of flooded areas caused by Typhoon Yagi. And it's also to identify the high-risk flood areas focused for disaster mitigation and recovery efforts. Why it matters? Well, hopefully this can be used to enhance disaster preparedness, informs urban planning, and ultimately builds community resilience. More about Typhoon Yagi. It hit multiple countries in Southeast Asia in early September 2024 last year. This included countries like China, the Philippines, Laos, Thailand, and Myanmar. But the most significant impacts were in Vietnam. Typhoon Yagi was the strongest storm to strike Vietnam in 70 years, causing severe flooding and landslides. So here is the animation clip that I want to share. We're starting off with a low pressure area forming in the Philippines. And as it's picking up speed, measured in knots, it's becoming a tropical depression, and then a tropical storm. And as it's picking up speed, it's forming a typhoon into a strong typhoon, picking up more speed, becoming a very strong typhoon. And then now, as it's approaching South China and northeastern Vietnam, it's becoming a violent typhoon, the highest typhoon classification in terms of maximum speed. And now it hits northeastern Vietnam, making its first initial landfall on September 7th at 6 a.m. And then it slowly dissipates away. And here's a map of the Typhoon Yagi's path and timeline. Notice the color-coded scheme here, blue for tropical depression, that started in September 1st, and is progressing through green for tropical storm, yellow for severe tropical storm, orange for strong typhoon, and then a darker orange for very strong typhoon, and then becoming the highest typhoon classification of violent typhoon as it reaches landfall in northeastern Vietnam on September 7th, 2024. So highlighted in green and blue, those areas are my study area, and they are Quang Ninh Province and Haiphong City. Now, a province has multiple cities within that province, where Haiphong City, which I will show, just has the districts. So here are the districts and the different neighborhoods in Haiphong City. And then with Quang Ninh Province, we have about 12 cities that are shown along with their neighborhoods. And so with these, there are coastal cities or coastal provinces, and these are factors to consider when assessing flood risk. And finally, this final map just displays when Typhoon Yagi first made that landfall, and it's showing that it's within Ha Long City of Quang Ninh Province. And I wanted to display all these neighboring cities and neighboring districts along with who are affected the most. So this is why I chose these two areas to be my study area. Okay, so before diving into our flood impact assessment, I like to explain why I chose Sentinel-1 satellite imagery for this analysis. So Sentinel-1 uses synthetic aperture radar, or SAR, which is an active remote sensing technology. And this technology is powerful because it can capture high-resolution images regardless of cloud cover, precipitation, or whatever it's day or night, making it more ideal for monitoring dynamic events like floods, where optical sensors might fail due to heavy cloud cover or darkness. So by leveraging both pre and post-crisis images from Sentinel-1, I can detect changes in the landscape, specifically highlighting the areas impacted by flooding. So here is a workflow of how I process the Sentinel-1 images using a software called Snap. And it's crucial for identifying the flood impacts. So we're starting off with the Sentinel-1 radar images that captures both the before and after flood events. And then I perform pre-processing steps. So the pre-processing steps involve multi-looking, which reduces speckle noise by averaging multiple looks of radar data. Then I use something called calibration, which is a technique that converts raw digital numbers into physically meaningful backscatter coefficients. And then after that, I use terrain correction, where I inputted a digital elevation model to correct the geometric distortions induced by the terrain effects. And one of the last steps in my pre-processing stage, I converted the linear backscatter values to decibels in order to enhance the dynamic range and for interpretation. So at the end of the pre-processing steps, in order to extract and identify the flooded areas, I subtracted the pre-crisis imagery from the post-crisis imagery to highlight areas of flood-induced change. Here is the final product. This map presents the results of my flood impact analysis. It shows the areas where flooding occurred highlighted in red. And what's important is, as we see the initial landfall at 6 a.m., notice that it's the southwestern region of Quang province highlighted in green that were severely impacted, whereas all the districts in Haiphong City were severely impacted. So in order to understand more, I created a choropleth map and a data visualization to understand which cities were affected the most in Quang province. So in bright, bold red, we can see that Hai Long City has the largest flooded area, measuring approximately 21.23 square kilometers, while Bin Lu, all the way up here at the top, away from Typhoon Yagi's path, we can see that it has the smallest total flooded area, measuring less than 1 square kilometers. And then taking a look at the total areas of flood in Haiphong City, we are seeing Tui Win and Cat Hai, an island off the coast of Haiphong City, to have the largest flooded areas, around 12.3 square kilometers each. So that's this bar graph and this one. Whereas Do Sung, hidden away in the southeastern region of Haiphong City, it had the smallest flooded area, measuring less than 1 square kilometer. So that was the first part of my analysis in this project. And then the second part is to identify the high flood risk areas in both of these regions. Here comes weighted sum analysis. This method is a form of multi-criteria decision analysis where I aggregated several different environmental factors by assigning each a weight that reflects its relative importance in contributing to flood risk. And then after that, I put those variables into my model to identify the high risk flooded areas. So this is a collage of 8 maps. The first one just gives you regional context, but I use 7 different predictive variables for my risk model. The digital elevation model captures the topographic variations that influence water flow. And then with the terrain slope, it's important because steeper slopes affect runoff and water accumulation. Whereas the drainage density, we are seeing how concentrated the drainage systems are, which can influence flooding behavior. With land cover classifications, it helps distinguish between permeable and impervious surfaces, critical for modeling water absorption. And then with the monthly total rainfall, this is coming from September 2024, we're seeing that it quantifies the precipitation that drives the flood event. And then with distance to road, we are seeing that it serves as a proxy for infrastructural accessibility and potential exposure. And distance to rivers directly relates to natural water flow pathways where proximity can increase flood risk. And so after having the variables, some of them were vectors as well, some of them were rasters. I had to convert all of them into raster format and then project them into a UTM 48 North projector system so that it can be measured in meters. And then, square kilometers. And then I also reclassified each of them to have a risk rank from very low to very high. And then I assign a weight for each. So digital elevation model, 20%, terrain slope, 15%, land, drainage density, 15%, land cover classification, 10%, the total rainfall for that month, 25%, because it's the most influential factor in flood formation. Distance to road, 5%, distance to river, 10%. So inputting those predictive variables with their weights into the flood risk models, we get this final product. So this map uses a color-coded scheme to represent different levels of flood risk. Dark green for very low, light green for low, yellow for moderate, orange for high, and red for very high. So we are only interested in the regions that are red and orange. And this final product pinpoints the areas most vulnerable to future floods and is a valuable tool for disaster preparedness and urban planning. And so with this bar graph, this represents all the total flooded areas that are considered high risk and very high risk within Quang Ninh province. Right off the bat, we can see that Hai Long City having the largest flooded area due to Typhoon Yagi's rainfall impact, low elevation, gentle slopes, and proximity to drainage courses, increasing flood risk. Whereas Quang Yen, also ranking in second, has a similar conditions. Conversely, Binlu's small flooded area all the way over here indicates its higher elevation or better drainage systems that mitigates flood accumulation. And then with Haiphong City, we are seeing that the district of Tuy Nguyen having a total flooded area of 237.26 square kilometers of very high risk. Now, this could be due to factors of low elevation, flat terrain, and limited natural drainage systems. And this will result in prolonged water accumulation. In contrast, districts like Lechan and Ngo Huynh have approximately 11 square kilometers each. Now, these districts benefit from higher elevations and more effective drainage pathways, which reduce flood risk. And so in conclusion, with my project, I used two different approaches, integrating them together. I used Sentinel-1 satellite imagery for flood detection, along with the 7 different predictive variables to build my risk model. And for applications, this will support disaster response planning, evacuation strategies, and infrastructure resilience for flood-prone areas. The limitations, of course, I lacked ground validation data, ground truths. I need to verify if the flooded areas I detect were actually accurate. And then I also rely too much on fixed environmental assumptions, which may not fully capture urban flooding complexities. And so for my future work, I would like to work with a flood database and be able to pull in ground truth data to verify my results. And then for my risk modeling, I would like to expand on predictive variables using cross-validation for the different weights and adding in more data. Hopefully that will improve flood detection as well as flood risk modeling. And so I guess in the future, I would also like to build an interactive web map for urban disaster planning as well. And that marks the end of my presentation. Thank you so much.